Binary lifting preprocesses a rooted tree so we can move upward in large jumps. After an O of n log n build, many tree queries take only O of log n time. The classic applications are lowest common ancestor and kth ancestor. Given two nodes, find where their upward paths meet, or find the node a fixed number of edges above a leaf. We store a jump table. Up at row v, column k is the ancestor of v reached by climbing exactly 2 to the k edges toward the root. Column 0 is just the immediate parent pointer. To climb d edges upward, write d in binary and use the set bits as jump sizes. 8 plus 4 plus 1 means 3 table lookups instead of 13 parent steps. The tree must stay static while we query. If edges change, rebuild the table or pick a dynamic structure instead. To pull off rapid teleportation up a tree, we must first allocate a blueprint called the parent grid. Instead of a single array that only points to a direct parent, every node in our tree is assigned a full row in a two-dimensional matrix. This layout allows each node to independently track its ancestors at increasing exponential scales, 1 step up, 2 steps up, and beyond. We initialize the table by filling in the very first column, where the jump power is 0. Because 2 raised to the power of 0 is simply 1, this column represents our immediate, direct parents. We discover these values through a standard depth-first traversal, anchoring our grid with a baseline mapping of the tree's physical edges. With our direct parents locked in, we can construct the remaining exponential columns dynamically without ever traversing the tree again. To find your ancestor 2 steps away, look up who sits 1 step away from your direct parent. Each new column is built from the previous one. That compounding rule lets the matrix trace deep ancestral paths in a single lookup chain. To determine exactly how many columns to allocate in our parent grid, we introduce a mathematical rule. The column count is based on the base 2 logarithm of the tree's maximum depth, plus 1. Depth counts edges from the root along the longest path. In this 9-node tree, maximum depth is 3. This formula shows we only need to allocate 2 columns, just enough exponential scale to jump from any leaf straight to the root. Now see how the formula adapts to an ultraflat star tree. Our total node count remains 9, but the longest path from the root to any leaf now has maximum depth of just 1. The formula scales our grid down instantly to only 1 column, index 0. Because no node is more than a single hop away from the root, wider exponential tracking columns are automatically stripped away. Finally, look at a completely skewed tree where our nodes form one long vertical line. The longest root-to-leaf path now has maximum depth 8 edges from root to leaf. Our formula tracks this depth expansion perfectly, widening our parent grid to 4 columns, stretching up to index 3. By anchoring our table dimensions dynamically to maximum depth, our layout stays perfectly optimized for memory regardless of the tree's shape. Now that our parent grid is built, how do we use it to jump an arbitrary distance? Suppose a query asks our cursor to climb up exactly 5 edges. Instead of looping 5 individual times, our algorithm looks at the number 5 through the lens of binary code. 5 breaks down beautifully into 4 plus 1, meaning we can conquer this entire distance in just 2 strategic leaps. We read our binary bits from largest to smallest. The first active bit represents a jump size of 4 edges. The algorithm instantly checks column index 2 of our parent grid for our current node, retrieves the ancestor sitting 4 levels above us, and teleports the cursor there in a single, constant time operation. With 4 steps cleared, the algorithm moves to the next active bit, which represents a jump size of 1. We look up column index 0 for our new position, take one final leap upward, and land exactly on our target ancestor. By breaking distances down into binary components, we can scale massive depths using only a tiny handful of high-speed jumps. Before we can search for a lowest common ancestor, our 2 nodes must stand on equal ground. If a query requests the LCA of two nodes at completely different levels, our first phase is to eliminate the depth disparity. By subtracting the shallower depth from the deeper depth, we calculate the exact vertical edge distance the lower node needs to climb. Using the power jumps we just learned, we feed this difference of 3 directly into our binary lifting logic. The algorithm sees 3 as a 2-step jump followed by a 1-step jump. It lifts the deeper node up by 2 levels, then by 1 more level, instantly erasing the vertical gap without wasting a single individual step. With the leaps executed, both nodes now sit at the exact same depth. If the deeper node happened to land directly on the higher node during this climb, our search would be over. But since they are parallel on separate branches, the playing field is officially leveled, setting the stage for both nodes to climb together toward their meeting point. Now that our nodes are perfectly level, we begin our final phase, climbing simultaneously to find their junction. We test our exponential jumps in reverse order, starting from our largest column down to 0. We want to take a leap only if it keeps the two nodes on separate branches. If a jump causes them to land on the exact same node, it means we've overshot our junction, and we reject the leap. Our 4-step jump lands both nodes on the route. Since they match, the algorithm rejects the jump and shrinks the leap window, stepping down to index 1, a jump size of 2. Testing this 2-step leap, we see the nodes land on completely different ancestors. This is a valid boundary step, so both cursors execute the jump together, leaping closer to the target. Finally, we check our last column at index 0, a jump size of 1. Because 1 step up would land them on the same node, this jump is also rejected, and our loop ends. By consistently leaping right up to the edge of the merging point without crossing it, we land precisely 1 step below our target. The absolute lowest common ancestor is now guaranteed to be the immediate parent of our cursors. Let n be the number of nodes in the tree and h the maximum depth. Preprocessing is order n log n, 1 depth first pass for parents, then we fill about log n columns for every node. Each LCA or KTH ancestor query is order log n, at most 1 table lookup per set bit. Space is order n log n for the jump table. The tree must stay static while we query, rebuild if edges change. Build takes the tree and a chosen route. First record how many nodes we have. Finding max depth is standard tree work, details omitted here. Column count is floor of log base 2 of max depth, plus 1. A depth first traversal fills parent and depth arrays, implementation omitted here. Column 0 stores every node's direct parent. Each node V gets its immediate parent in up, V, 0. Higher columns are filled in order from k equals 1 upward. Every node is updated in each column pass. Lookup mid is up, V, k-1, the previous column on the same row. That midpoint's previous column entry becomes up, V, k. Lift moves 1 node upward by a given number of edges. Walk k from the largest column index down to 0. When bit k of the step count is set, take that jump. Replace the node with the ancestor stored at up, node, k. Return the final position after all set bits. LCA finds where 2 node paths toward the route meet. If the first node is shallower, swap the labels. Ensure the deeper node is always in U. Compute how many edges deeper U sits. Call lift to bring you up to V's depth. If both pointers landed on the same node, that is the answer. Return that common ancestor immediately. Otherwise scan columns from large jumps down to single steps. Skip a jump when up, U, k, and up, V, k, would be equal. When a jump is safe, move U up 1 big step. Move V up by the same amount in parallel. When the loop ends, parent of U is the lowest common ancestor.